A seed distribution consists in how well the distribution of a given seed distance tends to an ideal measurement, called here xref. Plants that are too close to each other compete for resources, and plants that are far apart are not using all the available resources. ISO 7256-4/1 defines a standard for measuring seed distributions. According to the ISO, plants that have a distance greater than 1.5 times xref are considered false, and plants that have a distance lower than 0.5 times xref are considered doubles. Plants that fit in the range 0.5 xref to 1.5 xref are considered regular. Also, according to the ISO, the percentage of doubles and false and the coefficient of variation of the distance between each pair of plants indicates how well the distribution is. An ideal distribution would have 0% of doubles, 0% of false, and a coefficient of variation that tends to 0. We propose a software that aims to automate the process of quantifying the seed distribution, since it is prone to human error and it is time-consuming. The software targets two platforms, Android and Raspberry Pi. We studied the viability of Python applications in embedded systems in comparison with the Android application, that is used as a base, since from prior work, the performance of the Android version was deemed good. We analyzed the performance of Python as an embedded programming language, as well as how different models of the Kalman filter and Hungarian algorithm perform in an embedded environment, and if they have a larger effect in the tracker performance. The system can be broken down into three main parts: feature extraction, object tracking, and result processing. As can be seen on the image, each frame is extracted from the camera or video. Then each seed is tracked and the distance between two seed pairs is kept. At the end of the process, the relevant results are displayed to the user. During the step of feature extraction, a frame is retrieved from the video stream or a camera stream. To extract its seed position from the background, a color segmentation process was used. Firstly, the frame is converted to the HSV color space. Next, a binary image is generated using a lower and upper interval that corresponds to the interval of the seed color in the HSV color space. This interval is calibrated by the user. For tracking, the initial solutions of the software used the source tracker that was proposed by Billy. With testing, it was established that the model did not fit our performance needs and was re-implemented. The main change was the use of the Euclidean distance as a weight estimator for the Hungarian algorithm. More on that later. Here you can see the results screen of the Android version of the application. During tracking, each seed is given a unique ID and the distance of each seed, and the next seed is detected and stored with the IDs of the pair. The number of measurements is also kept to remove false positive detections. The cumulative distance and number of measurements of each pair is then used to generate percentages of doubles, false, and the coefficient of variation. The Android version of the system was implemented in Java and uses the OpenCV library for image processing. The embedded version, which runs in the Raspberry Pi platform, was implemented in Python using OpenCV and NumPy. On the right, you can see the setup used for the Raspberry Pi, using a webcam as input for the tracker. On the left, you can see the Python version running in the Raspberry Pi. And on the right, you can see the Android version running in a smartphone. First, the user inputs the color of the seed, then he inputs the ideal distance of the distribution, and calibrates the distance using a known distance as a reference. We established various points on the tracking step of the software that could generate performance gains in the Raspberry platform, those being a new model which only uses the center of the bounding box as the model for the Kalman filter. On the left, the old Kalman filter model based on the bounding box of the object, and on the right, the new one based on the centroid of the object. Two new distance estimators for calculating the weight for the association between each tracker and detection for the Hungarian algorithm, a Manhattan distance and the combination of the intersection over unit and the Euclidean distance. These are used as a weight estimator for the Hungarian algorithm and affect the association of the detection, the green rectangle, and the common filter prediction, the red rectangle. To compare the performance of the embedded solution versus the Android, a test using two different seed distributions was performed. The first distribution consists of a uniform distribution of 11 seeds. The second distribution consists of a non-uniform distribution of 11 seeds. To test how the different modes of the common filter and weight estimators for the Hungarian algorithm affect the performance of the solution, a test comprised of a non-uniform distribution of 11 seeds was executed, consisting of a pre-recorded video of a distribution. Contrary to expectation, the intersection of unit Euclidean model had a decrease in performance, and both Euclidean and Manhattan distance weight estimator had equal performance. Our trackers had the same number of frames per second. We suspect that this could be a bottleneck in the method read from the video capture class of the OpenCV API. The overall performance of the tracker can be attributed to the video, which contains a jump forward and two seeds that are very close to each other and can be wrongly interpreted as one seed. As can be seen on table 2 and 3, both Android and Raspberry applications had excellent performance in computing the seed distribution of uniform and non-uniform distributions, the limiting factor for the Raspberry Pi application being the hardware, in this case the webcam used.